Okay, good afternoon. 12 o'clock. Let's get started. Welcome to is it lecture 17, I believe, in Comborg. It's a beautiful day outside, and it's Friday again. So TGIF, everybody. How you folks are doing? Good, good, excellent. Yeah, and some people are asking about question 8. So yeah, I'd be more than willing to go over that question in office hours, or any of the days can do that as well. So just stop by in office hours. And yes, but it would have to be done. So if you want me to provide a solution, that would have to be done in after the late days period is over. So not today. So Monday or any day after Monday, right? Because people who are using their late days, they might still submit their work for this homework that was due last night. So, but of course, if you have questions that I can answer without telling you what solution is, then of course I'd be more than glad to answer those questions in office hours. Today, as usual, my office hours are 2:30 p.m. to 3:50 p.m. and yeah, so I'll be rushing to campus right after this lecture. And I can see our panelists are here. At least I can see that three of them are here. So I thought we were going to have more panelists today. So according to my records, we were supposed to have 5 panelists today. So hopefully the other 2 people are also here or will show up very soon. All right, and yeah, I'm just looking at your responses. Good but tired. I can definitely relate to it. I'm tired too. So I definitely I'm with you on this one, definitely. All right, so let me start sharing something just to keep you entertained. And all right, and let me again drag all my windows because Webex never remembers them. All right, come on, Webex. And I want to look at Q&A, and I want to look at chat at the same time. Yeah, and someone says they can volunteer to be a panelist if we don't have all the people who were selected. So let's see how many questions we get in Q&A, and then Liam, if we need a volunteer, I will definitely make you a panelist. And there are more people. All right, because like I think last lecture we only had 4 questions in the Q&A. So if the numbers are similar this lecture, we don't even need 3 people. So let's see how everything goes. And panelists, if you see that there are many questions and you feel overwhelmed, overloaded, then just just let me know. Okay. And so homework 4 was due last night, as I mentioned, and we will start grading next week because some people are, well, for one, some people are still submitting. And just a reminder, some people have as many as 6 late days in total, right? Because they earned 3 extra late days already. And besides, we are actually still grading test 4. We are not even halfway done, unfortunately. It's going pretty slowly, but we are hoping to make more progress over the weekend. And I believe our current ETA, our hope is to get, as usual, to get the grades for the test released before the next test, which is going to be next week on Wednesday, by the way. And so the scope, I think we limited to chapter 3. So that's our goal, to finish with chapter 3 appendix B today. And we might have time to start with chapter 4, but I kind of doubt it. So in any case, chapter 4, even if we started today, we will not be on this upcoming test. And we definitely are going to start chapter 4 on Tuesday, but like I said, it's not going to be on this upcoming test. So yeah, basically everything that was not covered in their previous exam, starting from that point up to what we discussed today for Chapter 3, Appendix B. So those are all their slides with Chapter 3 in them. So both A and B. So whatever is left off A and everything that we've covered in B. Okay, and homework 5, I actually have it written. It's right here. I didn't post it yet. I want to, do one additional round of proofreading before I open it to you, but I will do it tonight. And so homework 5 will be posted. And yeah, so that's C code pretty much entirely. So the only TA grading part would be just comments and style and all that kind of stuff. So it's a small portion of their grade, but yes, you will be building your own compiler for MIPS. So C to MIPS compiler. All right, so that's homework 5 coming up tonight, and I will also post practice problems for the test. I will try to do it tonight, but it's probably not very likely because I will be finishing up with homework 5. So most likely I will do it tomorrow. Okay. And so that's pretty much it. So you had lab list. Well, this week, 2 days ago on Wednesday, and yeah, how did you like that lab? Fun lab. Lab was easy. Lab was good. Okay. Cool. Okay. So maybe we can. Yeah, I'm thinking about kind of expanding this lab and using it, or the idea behind that lab in a team project. So since you seem to be in favor of what you did in that lab, it might be a good idea. Yes, you couldn't use if statements because that was the whole idea, right? So you build a simulator. So that was supposed to, yeah, and your lab TA's mentors were supposed to let you know that the idea is not just to write C code, but to write a simulator. Can we make a calculator for our project? That's an interesting idea. But a programmable calculator purely in open circuits or something similar. Is that what you mean by a calculator? Like a little computer with its own language, very limited. Add, subtract. Move from, load from memory, store from memory. That would be interesting. I agree with you. But I need to think if we can. Build calculator in Minecraft. I like this one. Although I don't have a Minecraft account, I have to confess. All right. Oh, it's free. I thought you need to kind of subscribe and get. Yeah, so it's $30. I wonder if the department would pay for my Minecraft. I don't know if I have enough courage to ask the department head. Probably not. All right. Anyways, yeah. Jokes aside, so we need to finish with chapter 3, and yeah, let's do it. So last time, I think that's where we left off, more or less. And okay, all right, so let me move my windows again so that I can see the slides. All right, so the normal numbers, that's the special cases where there is no hidden bit. So the hidden bit, normally for normalized numbers would be 1, and then we would take this 1, and because it's 1, we would have this decimal dot, or dot that separates the integer part from the fractional part immediately to the right of that hidden 1. So for normalized numbers, we would have this 1 dot, okay, and then we would append the fraction here, and we would call it significand. second, right? So, and that was for normalized numbers. And it was a few slides ago, so you can easily find this, of course. All right, so for numbers that are not normalized, or for numbers that we cannot normalize, we have to come up with something different, and this is exactly what we are coming up with. So it's just 0. This hidden bit is 0, and that's why we basically have this dot 0 dot fraction. Right. So in other words, we add 0, which effectively doesn't change the number, of course, but this is what our fraction is appended as before to the right of the dot, but now it's 0 dot fraction, and it's still called significant, but of course the value is going to be different than it would be for normalized numbers. And so then we obviously need to know whether we have a normalized number or not, because if you're just looking at the fraction, it doesn't have this information about whether the number is normalized or not, right? Because this is encoded in whether we have a hidden bit of 1 or 0, but the hidden bit is called hidden for a reason. It's hidden. It's not stored in memory. It's not part of the actual bit sequence that is stored in memory, and that's why we have to come up with some kind of convention that would tell us whether the number is normalized or not, and the convention is using this special value for the exponent, which is all zeros. And if you see an exponent which is all zeros, you know that it means that the hidden bit is 0, which means it's a denormal number, a number that is and cannot be normalized. And so why can we use that, and why do we need that? Well, for one, we can use this concept to encode 0, and there are two representations of 0, plus and minus. It's very similar to what we discussed several lectures ago when we were talking about representing negative numbers and their sign magnitude notation, SME. And so that's one case, but there are also cases where we want, when there is what is known as underflow with diminishing precision. So what is an overflow and underflow? Overflow is something that we discussed before, and overflow is when we have the result that is too large to fit into however many bits we use for representation. In other words, it just falls out of the range. Remember when we were playing with 4-bit integers, and we had an integer which so let's assume it is an unsigned integer, right? So it would be 15 decimal, and then if we add 1, we will end up with this number, which is supposed to be 16, but with 4 bits, right, we kind of see 0, and then we say, well, it's an overflow, exactly, because there's no way you can represent 16 using just 4 bits. Okay, so that's overflow. And underflow is kind of exactly the opposite. Well, what do you mean? You may ask, what would I mean the opposite? Is it like the same as overflow, but with a negative sign? No, negative sign doesn't change anything in that sense. It will still be overflow, right? Because it would still mean that the number does not fit the number of bits we have for that number. Underflow is the opposite, because it is basically the loss of precision, right? So this is the diminishing precision, exactly as this slide says. So imagine that we have integers, and you need to represent this number in decimal, okay? So obviously your choices, and imagine you have only 4 bits, right? Your choices are, well, you can represent it as a plain 0, or you can represent it as 1, or you can represent it as 2, and so forth. And obviously there is no way to represent this number 1,000th exactly. So no matter how you represent this number, there's going to be an error meaning the difference between the number as it is represented and the true number, the original number that you were asked to represent. So if we are only limited to integers, then of course you will select 0, 0, 0, 0, this bit sequence, which would correspond to 0 decimal, but it would be the closest representation of this 1,000th that you can get, right? Because the error would be minimal. If you go with 0,001, which is 1, the error, the difference between 1 and 0.001 would be larger. Okay, if we use 0,000, which is 0, the error, the representation error would be the smallest, and that's why we go with this representation. So you can just use you can use this idea further. Say, all right, we learned last time about fixed point. Okay, so we can say, well, we have, oops, that's the representation that we have. Let's say 4 bits of integer part, and then 2 bits of their decimal part, and it's fixed point, so it's always 2 bits to the right of the point. And then, as we were discussing, the weights of those bits would be 1/2 and 1/4. Okay, so if I have the same kind of task, but now with a fixed point, then I have, and let's say I want to represent 0.6 decimal. Okay, then the answer might not be as obvious as it was in the previous case. So we still have 0, 0, 0. Well, obviously, we start with trying their integer part to be all zeros, and then 0, 0, and then 0, 1, and then 1, 0, and then 1, 1, and then the next one would be 0, 0, 0, 1 dot 0, 0, right? And so those fixed point values would correspond to decimal value 0, 0 0.25, 0.5, 0.75, and 1.0. And then we still have to solve the same task. What is their number, right? 0.6 is not in our list, so we have to select the number that would be closest to 0.6, regardless of the sign of their difference, right? We just want the closest so that the absolute value of the error is minimal. And obviously, if I did my math correctly, it would be 0.5, right? Because then the error is just 1/10, 0.1, and that's the smallest error that we can get. And so we decide that we do exactly this. Okay, so now the question then becomes, all right, what if our value is, like in our previous example, falls here between the plain 0, like in this in this range, and the first non-zero number, like in with integers, that would be between 0 and 1. With this fixed point format that we used in the previous example, that would be between 0 and 0.25. So if the number that we want to represent is such that we have to use 0 to get their smallest error, then essentially, instead of representing something like 0.1, right, we need to represent, let's say, 0.1, and we use just this plain 0 to do that. Okay, so obviously it's a loss of precision, right? Because our current method of that we selected to represent numbers is just not capable of doing 0.1. The closest it can do is 0.0, so we essentially lost precision, and that is what is called underflow. Okay, and yeah, so that's the idea behind underflow. All right. And yeah, there was that pop quiz, and yeah, so we can actually go back to that poll and quickly go through the answers. So view results, that one was, yeah, and that was exactly, yeah, and note how submitted shows, it is tried to be smart when it shows their answers, but it is very confusing because it shows as 0 and 1, whereas the real options were, and I'll look them up, were those. So it's not showing options, that no one voted for, okay? But it shows just 1 and 0, okay? So And I think the majority of people voted for 0, which is, I believe, the correct answer. But we can actually submit it. It is now very, very advanced. It allows me to do actual queries against the database so that we can double check data if histogram is not looking very convincing. So it's poll number 56. So I just need to put my 56 here and 56 here. Then run this query. And we indeed can see that, well, yeah, actually a few people voted for other options. We can see it from the responses. Yeah, well, students do not have access to this toolbox for one, and then I'm pretty sure Submit is protected from drop tables or SQL injection attack or anything like that. All right, so yeah, 61 people voted for 0.0, and I believe that is the correct answer. So we were able to verify that, and that was poll number 2. And poll number 1, I think it was. Okay, so it was voting for the most helpful student, and I posted a message on a Submittee forum congratulating Sean. So Sean got the most votes, 28. Good job, Sean. And but all other people got a fair number of votes. So I gave 1%, 1 percentage point towards the overall course grade to all those people. Well, except Janshi. Janshi is actually one of our mentors. So their name was here by mistake. So all 6 students, real students, got 1 percentage point towards their overall course grade. It's already in rainbow grades. And if you're not if you're one of them, just keep doing the same great job, and try to be even more active and earn the second point for the second half of the semester. And people who are not in this list, of course, it's not too late. You can still be more active on the Submittee forum, helping other students, and earn 1 point for the second half of the semester. Okay, so that was that. Lecture 15, poll 1. What was lecture 15, poll 1? Oh, I think we discussed this last time. Yeah, it's going to be problem 1 for extra credit on the last test. So that was the question. All right, and so let me go back to where we were. All right, and then infinities and nans, not in numbers. We also talked about last time. So when the exponent is this another special value all at once, it corresponds to either infinity or not a number. So infinity, how do you know it's infinity? The exponent is all ones, and the fraction is all zeros. And obviously the sign then defines whether it's positive infinity or negative infinity. So when we do, some non-zero value divided by 0, you get infinity, depending on the sign of whatever you were dividing by 0. Whether if that sign was positive, you get positive infinity. If it's negative infinity. And of course, sometimes when you divide by even a non-zero, you might get an infinity because you might get a loss of precision. So and then the closest value would be infinity. Okay, and then if exponent is all ones but fraction is not all zeros, then it's not a number. This is something that you get if you take a square root of a negative number or if you divide 0 by 0. Okay, so the result is basically not a real number, and that's exactly what nan means. And as far as performing operations on floating point values are concerned, nan is a valid argument, so it can be used in subsequent calculations. But nan with any operation. So if you perform any operation and one of the arguments is nan, then the result is always going to be nan. That's why nan is kind of sticky, right? If you do nan, plus 5.5, it's still going to be nan. right? So you cannot really get rid of nan normally by just performing operations. So once you get nan, then the rest of the operations in the chain of operations are going to be they're going to result in nan as well. Nan is a fun acronym. Yeah, I agree. Number. All right. So now let's talk about the operations that we can perform on floating point numbers. Obviously, they are a lot more complicated than on integers. And the reason for that is because instead of just a single bit sequence, which was like, our two's complement notation that we talked about before, just one field, and we do our grade school addition algorithm on on those bits, just remembering that it's a binary system. And so if we do, if we have 1 plus 1, it's not going to be 2, it's going to be 1, 0. Okay, so just remembering that, we could do all our standard math easily. With floating point, it's more complicated because we actually have 3 components. We have the sign, we have their exponent, and we have their fraction. And therefore, the procedure, even for addition, is slightly more complicated. So let's go through an example. Imagine we have this 4-digit decimal example. It's actually a very useful analogy when thinking about performing addition using IEEE 754. Just think about how you would do a similar addition using your decimal system, and then just translate it to to binary. So it's completely analogous. So first you need to make sure that you align decimal points, right? If you have different exponents like here, you cannot just start summing up 1.61 and 9.999, right? Because the dot is not in the same position because of different exponents. So first you have to shift one of their numbers so that it aligns its decimal point with the other argument. So we do exactly this. We shift number with a smaller exponent so that they align. In this case, the smaller exponent is 10 to the negative first, and we shift that number so that the exponent is the same as for the other number, 10 to the first, and that means that we have to shift by 2 positions. So 1.6 becomes 0.016. So now that the exponents are the same, which means the numbers are aligned, we can just add the significance, right? We can add 9.999 and 0.016, and when we do that, we get the sum. And of course, the exponent is not changed when we just add the significance, so the exponent is the same. And then, of course, this number is not guaranteed to be normalized. Remember, normalized means that it's between 1 and so it can be 1 or more, so greater or equal than 1, and strictly less than 10. Obviously, our significant is not strictly less than 10, so it's not normalized, and we need to normalize it. How do we do that? Well, we shift the point so that our significant is normalized, and we need to remember by how many positions we shifted our dot, our period, because it would mean the amount of adjustment to the exponent that we need to do to compensate for us moving the dot around. So we have to move the dot 1 position to the left so that our significant is greater or equal than 1 and strictly less than 10. So we moved to the left 1 position, which means that we need to add that 1 to their exponent. And here we are. So it's 1.0015 times 10 to the second. And we are almost done, but not quite done, because it turns out that this number cannot be represented exactly using the number of digits that we had at our disposal to begin with. Okay, we have only 4 digits, and this result is 5 digits, right? Those zeros here, they are significant zeros, right? We cannot just get rid of them because they are in the middle of the number, right? If we had something like 001 point something, of course, the leading zeros we can ignore, but those zeros in the middle, we cannot ignore. They are significant, and that means that we need 5 digits, which we don't have, because it says we have only 4 digits here. And that means that we have to, kind of select the closest value that we can represent. again, there will be a representation error. It's inevitable because we always have a finite number of digits. Even if we had more than 4, it would still be not sufficient for some computations, right? It would still be a possibility that we end up with needing more digits that we were given. So in this case, we go with 1.002, or we could have, we could have basically gone with 1.001. The error would be the same. It doesn't really matter in this case, how you round. There are actually different rounding methods. So some as you might have heard about the so-called bankers rounding, where the value is actually rounded towards small. So this 0.5, right, is the problem. Like, where do we round 5? Because it's exactly halfway from both ends, right? We can round it to 1, we can round it to 2. The margin of the error margin would be the same, and that's why there are different rounding methods. So one very simple that you probably learned in middle school or even elementary school says 5 always rounds up, but there's another method called Banker's method, where that 5 rounds either down or up depending on whether this digit is even or odd, and that actually gives a much better rounding method because it's more balanced. You don't always round up. You round up 50% of the time and round down 50% of the time, so it's overall more balanced. So in any case, all right, that's the number that we can represent. So here, let's assume that we use their elementary school rounding, where 5 is always rounded up. So it's 1.002, and of course their exponents stay the same. So here we are with floating point addition. All right, and yes, floating point arithmetic is quite expensive, and well, expensive means it's slow, and therefore, we will see shortly that in many cases it cannot be executed. Most floating point operations cannot be executed in a single cycle, whereas all other instructions that we've covered can be executed in one cycle. And that's our next topic coming up. We will look at their internals of a processor, at everything, at all their hardware that makes up the processor, and all the timing diagrams that show how long operations are taking, how they are performed. And that's actually the sacred knowledge that I'm hoping you enjoy in this class, how computers really compute, how that computational magic happens. Is it possible to implement it with a single cycle, though? It would be possible. Pretty much nothing is impossible. Well, I'm exaggerating, but in this case, it would be possible. But then the question is the price you would have to pay for it. So you either have to throw in a lot of additional hardware, and I mean like a lot, to make it as fast as let's say integer operations, or you would have to actually select their clock cycle for your entire processor to match the slowest operation, the floating point operation. And that means that, yes, your floating point operations will be taking 1 clock cycle, but then, and it means that all other operations would be also taking the same clock cycle. Whereas they actually are using, maybe, 10, 20, 50% only of that clock cycle. So they have a potential of running a lot faster, but you're selecting like the common denominator, right? You are selecting your clock cycle based on the slowest instruction. And if you do that, taking floating point as your slowest instruction, then of course, essentially you're slowing down your overall program, hypothetical program, right? Because floating point operations do not happen, they do not make up 100% of all instructions executed. Okay, so that's why in many processor designs, floating point is completely separate from the regular processor. So you might have heard the term coprocessor, And that's exactly what MIPS architecture is using. So floating point operations are done by a separate coprocessor, which has its own separate clock, and then it just kind of talks to the main processor, to the processor that does all other instructions, including integer arithmetic instructions. All those other instructions run fast in one short clock cycle, whereas the floating point instructions run in multiple clock cycles of their main processor. All right. So yes, and some modern desktop CPUs do both floating point and integer additions in one cycle. That can be done, but it requires, like I said, additional hardware, and that hardware costs money, right? So, one thing, if you are building a CPU for a gaming for a gaming desktop or some other high performance desktop where you could sell a processor for $500, and people would eagerly buy a CPU for $500. That's one thing. But what if you are designing a processor that needs to run a washing machine, and your entire washing machine is I don't know, $300, and their constraints are your processor should not cost more than $2. Okay, so then of course it's a totally different story. All right, so it's all technology and economics and finances and marketing too. All right. Anyways, so we take the same idea that we just went over with an example of decimal numbers and just apply it directly to our IEEE 754 to the binary representation of floating point values. And so here is an example. And what format is this? Well, it's not exactly a floating point. It is actually a fixed point. As you can see, we are also given a four-digit example, all right, 4 binary digits, and we need to add them, these two values. And so this is the sign. So one of the values is negative. And so first we have to make sure we align not decimal, binary points, right? Because we are in binary first. So we have to shift their smaller number and well, they're the smaller by absolute value. So this negative 0.14375. So that exponents are the same, -1, and that means that their mantissas, or the fractions, are aligned, and that means that we can just add them, in a straightforward fashion. 1.000 and a negative 0.111, and that's the result. Okay, and of course the exponent stays the same. And then we normalize the result and check for overflow or underflow. So this value is not normalized, right? Because it's not between 1 and 2. So again, remember, for the binary case, their normalized means it has to be greater or equal than 1 and strictly less than 2. And this one is not greater or equal than 1. So we have to normalize so that it is, in this case, it becomes 1.000, and we had to shift by 3 positions our binary point. So we have to adjust the exponent, and that's it. There's no overflow, underflow. We are good. That's the result. And you know, step number 4 still applies. We need to round and renormalize if necessary, but in this case, we don't have to. Okay, so it's 1 times 1/16, right? 2 to the negative 4 is 1/16. So it's 1 times 1/16. So it is 0.0625. All right, so the adder hardware for floating point, as you can imagine, is going to be much more complex than integer adder. And, still doing it in 1 clock cycle would take too long. And because we would have to go with a longer clock cycle, as we just discussed, and much longer than integer operations, unless you go with a more advanced adder hardware. Okay, and So if you don't throw in that additional hardware, then it means that the slower clock for floating point, if you decide to go with just a single slower clock so that your FP operations execute in one clock cycle, it means basically that their CPU would be underutilized for all other instructions, effectively penalizing all other instructions. That could go much, much faster than this slow clock, but they cannot if we decided to go with that single slower clock. And that's why quite common FP hardware is designed such that it takes several clock cycles, or it has a separate clock separate from their main CPU, and then just floating point instructions signal their main CPU when the result is ready. All right, so this design, among other advantages, has a very nice feature that it can be pipelined, and we're going to be talking about pipeline. That's our next topic. And just to give you a perspective, this is their hardware for adding to floating point numbers, and as you can see, all right, so first observation, there's quite a few multiplexers. So multiplexers are very common. And yeah, there are two ALUs, big ALU and small ALU. And actually you can kind of track which hardware is used to perform each of the steps. So steps refer to the steps that we talked about in the previous slide. So first we need to compare exponent. So here is their ALU to compare exponents and perform and compute the difference. So it effectively performs sub of the exponents to decide which number needs to be shifted and by how much. And so we shift the smaller number to the right. So that's why there is this shift right thing, right? So it's a shifter. And note how the shifter gets its input from either, and let's call it operand A and operand B, either operand A or operand B, right? Because you see that they are both fed, both the fraction of A and the fraction of B are fed into this multiplexer, and then this multiplexer decides which is taken and routed to the shifter, right? Whether it's the fraction of A or the fraction of B, it is controlled. So blue in our slides in the textbook in Zybox, blue means it's a control signal. See this control circuitry, and it is drawn as an oval, as a sort of a black box, but you can imagine that it is just some logic gates that perform some Boolean function, right? So Boolean function, something like, if their exponent difference is such, then this control signal is 0. If it is something else, this control signal is 1, okay? Depending on their sign of their difference between the exponents, right? And that's how we know whether we need to shift their A or shift our B. Okay, so and we will see this kind of approach, high-level approach to control, where we just draw a black box for control signals, and then of course comes the moment when you need to implement this with real gates, right? You need to write all the Boolean functions for each of those control signals. And you did something similar for question 8 on last homework, right? Where you had to implement that overflow control box and actually decide how this overflow signal is produced, right? Basically to write a Boolean function that would be a function of all the inputs, and the output would be this overflow signal. So here it's the same idea, just a little bit more involved, because there are, as you can see, there are many outputs, there are many functions, there are many control signals that you need to produce. But the idea is the same. All right, so we shift their smaller number, so we align the binary points, then we add. So this is this big ALU that adds to fractions, and then we need to normalize. So basically it means shifting, and then we need to round, which basically means that we might need to increment or decrement our number. Okay, so this increment or decrement output is fed to the rounding hardware, and this is the end result. Okay, so that's That's the overall idea. That's the circuit for hardware edition. We're seeing a lot of unfamiliar hardware in this example. I don't think any of that is unfamiliar. So some of them are not, the implementation is not shown, okay, and but you should be able to produce all of that after some thinking. So ALUs we already talked about, and then all right, how is it controlling all the inverters? I don't see any inverters. I'm not sure what you're talking about. What are the inverters? To me, an inverter is an inverter is this. Is this? I don't see any of them in this diagram. And yeah, if you're talking about their subtraction, it's hidden inside the ALUs, right? So, oh, they're so you mean they're multiplexers? Yeah. So the multiplexers we talked about a lot, and it was actually in the previous exam, like build a 4-input multiplexer using 2-input multiplexers. Okay. So, and yeah, if you have questions, please feed it to our panelists. I think they're bored. They only had 4 questions so far, including the test question, which doesn't really count. So please let those people earn their quarter points. Okay, they're sitting there, waiting for your questions for them to answer. They cannot really, probably answer it in the chat. It scrolls too quickly. All right. So, for example, like shift left or right, right? So this, that you can also design just using the Boolean functions that we discussed. Some of the components, though, as we shall see shortly, you will need memory to implement them. Okay. So, for example, increment or decrement. So it's essentially a counter. So like this component. I don't think you can do it without memory, and we will talk about memory today. That's our plan. But let's move on so that we have time to cover everything. We have lots of exciting stuff I have prepared for you. Control is just the black box that has certain inputs. Those inputs are binary signals and certain outputs, where each output is a function of the inputs. So it's a so-called combinational circuit with no memory. And so imagine that circling back to their test. Imagine you had something like A2, A1, A0, and then output was D. So you were defining function, a Boolean function of 3 variables, A1, A0, right? And we call that function D, and you built a truth table, you did K-map minimization, and then you implemented this in hardware. So that's exactly the idea. You would put that hardware, in this box, inside this box, and do the same for all other functions. So you may use an encoder, but more likely than not, all you need to do is a bunch of AND, OR, and NOT gates. So it just, but an encoder is also inside, right? Under the hood is also a bunch of AND, OR, and NOT gates. So if you see that you can use an encoder efficiently, then of course you are allowed to use any combinational circuits, any components that we discussed already. Okay, and encoders can be very useful. So I had on a makeup exam, so people who had an excuse for Wednesday, an excuse absence for Wednesday, they were actually given a slightly different version of the test where they had for the last question they had to use an encoder, and so once I make sure that all makeup exams are done, I can show you that question and we can discuss the answer as well, right? Because that is exactly as you mentioned. Use an encoder to do something. Something. I think it was a pretty cool question. Remind me about it. I think you're gonna like it. Okay. All right, so let's move on to floating point multiplication. And again, here we can draw exact analogies between how we perform decimal multiplication with a fixed point and the same with a floating point. Okay, so here, and yeah, one comment that I wanted to make note that, well, what we are doing here in this example is actually a fixed point, okay, for their significance. But since we have those exponents, this is what defined. This is what defines a floating point. So, with fixed point, we would only have this, this fraction, right? This part without the exponent, and the position of this dot is going to be of this point is going to be fixed, and adding the exponent, right, that can vary is what makes it a floating point. Okay, so there's really, nothing, no mystery behind why is it floating point, because by changing this exponent, we can make this point that otherwise would be fixed, we can make it float, we can move it around. That's why it's floating point. Okay, but all their math, like, if we align the exponents, then all the math is exactly as it would be for a fixed point, and that makes things a little easier to handle. All right, so here's our example with decimals. All right, so we have these fractions and these exponents. We are multiplying. So first we add exponents, and here we need to remember that our exponents are biased, so they are stored not in a straightforward way in memory, but they are stored with bias added. So that means that when we want to perform arithmetic on those biased exponents, we have to subtract bias from it. And recall that for a single point, a single precision, it's 127. For double precision, it is 1023. And we do that in this example. So the new exponent is 5. And then we multiply the significance just using the grade school algorithm. And we get 10.212. And we already computed the exponent. It is 5. And then we just need to normalize the result and check for overflow, underflow, same as what we did for addition, and then round and renormalize if necessary. So here, obviously, if we only have 4 digits in our fraction, and that 4 includes their hidden bit, so you can see that in a normalized representation, this is always 1, right? If the number is normalized, so we don't really have to store it in the actual memory, so it's a so-called hidden 1. Okay, so we have, but if we count that hidden 1, we have 4 digits only. And then we determine the sign of the results just from the signs of the operands, because remember, we were ignoring the signs when we were multiplying significance. And of course, we need to determine the sign. So just, based off the signs of the arguments, and set this single bit S field in our IEEE 754 format to the correct sign of the result. And that's it. Do the same thing with binary, okay, with IEEE 754. Well, it's not IEEE 754 because it's not single precision, right? Remember that we only have 4 digits just for simplicity. In IEEE 754, we have a lot more bits to represent our fraction, okay, depending on their single or double precision, but in any case, it's a lot more than 3. But just for the example, of course, it makes it easier to handle. So we have to add exponents. First, we have to make sure that we subtract the bias. So unbiased exponents are these, okay? And if they were biased, so we had to add 127 to the exponents to make them biased, okay? And so then we have to account for this 127, and so the -3 plus 127 is going to be the biased exponent. So basically, you can compute unbiased and then -3 and then add the bias like that, or you can perform all your computations with biased exponents like shown here, Okay, and then because we are adding bias twice, you have to subtract 127 because you only need to add bias once for a single value. Okay, so it's as you can see, it's the same result, just different, slightly different ways to do it. Then we multiply significance, and that's the result. Again, just the same rules as in the grade school multiplication algorithm. Here we are only dealing with fixed point with fractions because we already took care about the exponents, and that's the result. And the exponent that we already computed, we just write it here. Then we normalize the result and check for overflow and underflow. It is already normalized because you can see it is between 1 and so it's greater or equal than 1 and strictly less than 2. So this is true. It's already normalized, and we don't need to round. But typically, we might have for other values, we might have to round and renormalize. But here we are done and just need to determine the sign because we were multiplying a positive value with a negative value. So the sign of the result is negative, and we just write this negative thing here. Yes, and as someone noticed, you can determine the sign of the product with just a single XOR gate, right? But if you're not sure how this is done, just draw a truth table, okay? And you have the sign of first, the sign of second. Those are your inputs, and then the sign of the result, and just and just do all combinations, right? Sign of first, sign of second, and then sign of the result, right? And then do just literally 0, 0, 0, 1, 1, 0, 1, 1, right? 0, 0, both arguments are positive, so the sign of the result is positive. 1 is negative, but only 1, so it's 1, it's 1. And if both are negative, then the result is positive, so it's 0. And here it is, exactly XOR, as someone mentioned. Yeah, here 2 is a subscript. All right, so floating point arithmetic hardware, as you can see, is complicated, and for the floating point multiplier, the hardware is a similar complexity to floating point adder. Okay, it uses a multiplier for significance instead of an adder, but other than that, conceptually, it's very similar. So typically, the hardware to perform arithmetic operations on floating point can do addition, subtraction, multiplication, division. That's pretty common, but also reciprocal, so 1 over value and the square root. And obviously, we have to be able to perform floating point to integer conversion. So if you have 5, you can turn it into 5.0 for the purposes of then performing operations on that 5 on in your floating point hardware. So that number in 2 is supposed to be 1.110. Okay. So yeah, so 2 here just means it's binary system to make sure that we're not mixing it with the decimal, right? Because here, so this is decimal, right? This is 10. So this is your real 1.11, right? So this is a decimal number. It only has ones, so you could get easily confused. Oh, is it a binary? No, this is decimal example, okay? And here it is binary example, so all values are binaries. Is there a typo? Could be in the result. Right. If you could, about step 2. Oh, here. Yeah, you're right. It is. Yeah, it is. It is. It has to be this, right? Because then it is written correctly here. So it is 1.110, and 2 is a subscript. Yeah, and actually, yeah, those slides come with a revised edition of the textbook. So as you can see, yeah, and let me put a note here, fix typo. Thank you. Thank you for being on top of things. Yeah, I was looking at it and I actually didn't notice. So whoever noticed, thank you. Good job. Was it Henry? Okay, yeah. Henry Charles, good job. Thank you. All right. Yeah, and as we discussed with addition, a floating point arithmetic can take several cycles, but it can be pipelined, so it's a good thing. All right, so now on to the interesting stuff. How do we use all that in our beloved MIPS? Okay, so please expect definitely on the next test a problem where you would need to write a MIPS program that performs floating point operations. Okay, it's pretty much inevitable. So, and that this is exactly what we're going to discuss right now. So, floating point hardware in MIPS is performed with a separate processor called coprocessor 1, so CP1. And as with the regular instructions or the instructions that we covered before, all operations in floating point are performed on the registers only, so no operations directly with memory locations. And therefore, there are separate dedicated floating point registers called FP registers. They have their names starting with F, so F0 to F31. And if you are doing single precision floating point, then you just use those registers because they are 32 bits, and this is exactly what matches the IEEE 754 for a single precision format. If you are doing double precision, then you need 64 bits, and the way it is done in MIPS, each register is paired with their friend, with their neighbor. So we have a pair of F0, F1. They are technically two registers, but for double precision, they act as a single 64-bit register. Okay, and they form those pairs, and pairs are fixed. So it is always a register with an even number and the following odd register. So it's F2, F3. You cannot have F1, F2. It's not a pair. It's always like that. F0, F1, and then F2, F3, and so forth. Yes, MIPS. This part of MIPS, floating point operations in MIPS, is going to be on the exam, and I know it's going to be, it might be harder because we didn't have a lab on this because we are only covering this material today. So there was no, there was no way to practice it in the lab. But I will post practice problems for the exams, and I will point you to the example that I wrote. It's kind of reminiscent of the example in the slides, but slightly expanded. And hopefully that would give you enough practice. It's really not that complicated. It's a bunch of new instructions, but you're welcome to use your creep sheets. You don't have to memorize those examples. Yeah, it's not so MIPS takes a while to write. This is true, but the problem on the exam is not going to be as big as problem one on the previous exam, so there will be less code to write. Conceptually, I hope you agree. It's just a few new instructions. It's a lot easier than stuff that you have already learned and mastered. Like if you ask me, the addressing modes and computing those, accessing arrays in memory and doing their offsets and also dealing with calling procedures is a lot more complicated than this. Here, you just need to know the instructions. Okay, and someone is jumping ahead, asking questions about the instructions. So let's talk about that. Floating point instructions operate only on those floating point registers. Okay, so those Fs. So they cannot access any of their other general purpose registers, which means that we have to move data from their from memory into specifically floating point registers. So remember, it's everything related to floating point is coprocessor 1, and C1 is actually it stands for coprocessor 1, C1, coprocessor 1. Right? So to load and store data, load from memory, store into memory, you use LW and SW, and then C1 just says that it's their coprocessor 1. So if you're preparing to do floating point, it's going to be C1 for you all the time. Okay, and yeah, here is an example. Load into register F8 of coprocessor 1 the value from memory pointed to by the address and stack pointer plus 32. Remember, this is a plus, right? This is a base address plus offset. So load word, so this is word as before, right? And this is double word, or 64 bits, okay? Or 8 bytes. So D stands for double. And that you need to do if you are planning on doing double precision. So this instruction in particular, LDC1F0, will actually write to both F8 and F9. So it will update 2 registers because for double precision, they form a pair. And let's, I don't know, let's imagine that our SP is, I don't know, 7FFF 000, just to make math easy. So here is our memory. And here is 7FFF 0000. Okay. And imagine that this is 1 byte. Our memory is byte addressable. So this is the first byte that will be read. Let's say, I don't know, it's 1C. And then the next byte, 2, 3, and so forth until we get to byte 8. So we will read with this single instruction, we will read 8 bytes from memory at once, and the first 4, 1, 2, 3, and let's draw the 4th one, right? We'll go to F8, and then, and there is an ellipsis, right? So the other 4 will go into F9. Okay, so we are reading 8 bytes from memory, loading into the pair of registers, F8, F9, and then we are ready to perform double precision arithmetic. Okay. To store double precision, we need 8 bytes and 4 bytes for single precision. That is correct. So when we allocate stack memory, we just watch out for that. Exactly. Yep. All right. So, and then, load and store instructions for words and double words we already discussed. Now we are ready to look at their arithmetic instructions. They are very straightforward. Hopefully you agree with me. Add, subtract, multiply, divide. Okay, and then this dot S means single precision, and this dot D means double precision. And it's a little weird, but dot is part of the instruction. So it is, you literally write add dot C. And here's an example, okay? And as before, here we are multiplying F6 and F1, or we are adding, because it's add instruction. So we are adding the contents in F1 and F6. It's single precision, so the entire floating point value fits into one register, F1 and F6, and the result is written to F0. And from there, you can store it from F0 into memory. Okay, multiplication, same idea. F4 is multiplied by F6, but now they are double precision. So you know that it's F4, F5 pair contains the first argument, F6, F7. So I will put here F5. Okay, and I would put here F7, right? You don't have to write it, all right? But you need to remember that, yeah, it's for double precision, 2 registers, a pair is used, right? So these 2 arguments are multiplied, and the result is written to F4, and we know that F4 makes a pair with F5. All right, so but add, subtract, multiply, divide are the same. So comparison, if you need to perform any conditional logic like your if, it's the C instruction, where C is for comparison. So hopefully easy to remember. C dot LTS. So LT is less than, S same single precision or double precision, C is compare. And instead of LT, you could use EQ, LE, and a bunch of others. You probably don't really need them, but EQ, LT, LE are the most common. Well, yeah, it might be necessary, but it's a mnemonic. Remember, mnemonic is something that helps us to memorize instructions, and they thought that having this C kind of reminds you of the compare, and it makes it easier to memorize. So in any case, you're not designing this MIPS ISA, so it has already been done, and you just need to memorize that. All right, and then so branch on floating point condition, whether it's true or false. So it's B for branch, C, and then 1T or 1F, right? So this is false. This is true. Okay, and yeah, so that's your branch instruction. Very straightforward. BC1T target label. Okay, so but this has to follow the compare. Okay, so this compare instruction, it sets or clears a special condition code bit. Right, you cannot directly access that condition code bit, but so it's not like it's different from the from the rest of MIPS that we learned, where SLT sets the register that you say it needs to set, or not set or clear. Here, it's a condition bit that is kind of not visible, directly visible to you, and this compare instruction sets or clears this special condition code. You can treat it as as a very small register that you cannot access directly, but you can set or clear it with a C instruction, and then you can analyze the state of that condition code, whether it's true or false, with their B instruction. So the integer part of the float is in F4 and the decimal part is in F5 with double precision. So to answer that question, and well, for one, it's not really important that much, but if you are curious exactly how the fields are partitioned, you can go to here, and you see that for the double precision, we have 1 bit of S and then 11 bits of exponent, and then 52 bits of fraction. So you see it's not divided like 32 and 32. Okay, so you cannot say that, if you think of it as 32 and 32, you cannot say that one is a fraction, another one is exponent. The fraction, actually, goes all the way up to here. So this is all fraction, right? 52 bits combined, and only 12 bits here, 1 bit for the sign, and 11 bits of this word are used for their sign and their exponent. All right, and here is an example that uses floating point. So, if I were you, I would be ready on the exam to write something similar, maybe with with a code to actually call this function. So, not as small of an example as here in the slides, but something along those lines where you need to perform some kind of floating point computation. So here the formula is given to you. It's just converting Fahrenheit to Celsius, all right, and the formula is here. And so first we need to decide where we store what. So there, and we decide, all right, so the Fahrenheit value is going to be in F12, and we're going to be using single precision arithmetic. floating point arithmetic, and the result is going to be in F0. Literals are in global memory space, and yeah, by the way, this is an example of using GP directly, to access memory locations. Okay, and so first we need to load into our coprocessor the values. So we load const5, so this value, okay, from memory into register 16. We load 9 into F18, and then we divide 5 by 9. So this is 5 divided by 9, and the result goes in F16. So we overwrite const5 because we no longer need it in this computation. So this is now in F16. And then we load 32 into register 18, our constant 32, and we subtract. So we perform F12 minus F18, and I believe this is it's Fahrenheit, right? So it's Fahrenheit minus 32 goes into F18. So it's this subtraction, and then we multiply F16, which is this thing here, by the result of F18, which is this thing here. So we multiply them, okay, to complete our formula. So this multiplication, and the result is in F0, and that's where we decided we want the result to be when we return. So return from the procedure as usual array. Should you save FP registers between procedures? So F registers can only be modified with those instructions, okay? But yes, they can be modified by any instruction that uses floating point. So if you, if you want to write their, if you want to practice defensive code writing, then you should be saving those registers if they are important. Okay, or you can just save them in memory. So you can, once you computed this F0, you can actually store it in memory. Okay, or if you want to keep that value returned to you by the procedure. And why are we loading with LWC2? Yeah, it's a typo. Thank you. It's all floating point is coprocessor 1, so it's a typo. Thank you. Another person who is on the lookout. All right. Practice exams will be posted tomorrow. I'll try to do it tonight, but like I said, I probably won't have enough time. Well, const5 is just a label, okay? So in this case, I will give you a real example that you can actually, let's actually look at that example. And it's here, it's under lecture exercises, right? So const5 is just a label, and you can actually run this example. It's a little bit more involved. It's a little, it's a few extra lines as compared to what you see on the slides, but it is the actual example that you can run. And if you run your Mars, why do we use F12 and not F2 for Fahrenheit? You could have used F2. No reason. It's an arbitrary choice. And Mars. You don't have to use GP. You can just load address with an LA instruction if you want. All right, and so let me see. We have 500, and I guess I didn't copy it here. So let me find it. Oops. Find it here. Notes. I think it's from the previous lecture. Nope. Yeah, it's from the previous lecture. Load. All right, and yeah. So let's let's see if this example works at all. So let me run it and see what is wrong. I suspect it is. Yeah, so it would work in QSPIM, but for the return from main doesn't work in Mars, so it's one of the differences in their simulators. So you just need to do syscall 10, I believe, and so we'll load immediate into A0, I believe, and then do syscall. So instead of JR. Right, and let me just check myself to make sure that I'm getting all their and where is it? 10 exit in V0. Okay, I thought I was not getting it right. So load immediate into V0, 10. Okay, and save it, and then we run it again, and yeah, you can see that it runs. So it uses fixed values, but we could also use read double, read float, read double. So those syscalls 6 and 7 to read the values in from the user. Here I'm just using fixed values, so 21.5 is in Fahrenheit is negative 5.8 ish, so it's pretty darn cold. So hopefully it's warmer than that today. Okay, and then if we try, I don't know, 61.5 and run it, and it's not too bad indeed. All right, so it's not too cold. It's 16.4 roughly degrees Celsius, so it's a little chilly, but not too bad. Okay, so that's yeah, maybe there is a way to configure Mars, as someone suggests, to not generate this error if we attempt to return from the main. Yeah, it's of little importance because for SPIM and for submiti, which runs SPIM, and QSPIM uses the same the same convention as SPIM, you need to return from RA, you need to return from main, but I believe that syscall 10 works in SPIM and the QSPIM equally well. I think so, but even if it doesn't, it's easy, depending on which tool you're using, to comment out the other side and uncomment out this one. So it's just the difference between simulators. It's really of very little importance. All right, and yeah, by the way, among the tools that Mars offers, here is the floating point representation thing, which I think is pretty cool. So, and there are, of course, tons of online tools that I'm sure some of you are using. But if we look at this 21.5, okay, so you can, see how it is actually represented. So this is Fahrenheit, okay, 21.5. So we compile, and then we need to find out where this value is stored in memory. So it's this address. I have it highlighted right now. Okay, and this is this address. And if you plug it into here, and what am I doing wrong? I'm not sure. It should be working. Okay, here we are. As you can see, it is 21.5. Okay, so and here you see the sign, the exponent, and it explains that the exponent is biased. So that's why we see this 131 minus 127 minus the bias, and here is the fraction. Okay, so and you can actually, you can actually look at their registers, see all those F registers, all 32 of them, and you can actually connect it to MIPS. So that's also a convenient feature. And if you change something, so let's say I want to change this to this, okay? And this would be 23.5, and I see that, oh, I just need to change A to B, all right? So, and I can edit my values here. So see how here I'm editing my memory value. Okay, I changed it, and yeah, and I can run my code with this new value. So you see how it says 23.5 right now. So you can use that to debug your MIPS code with floating point values, right? You can check the values. You now know how to decode them, and you can change them on the fly as you are debugging. All right, and sure, you can try inf, certainly. So tell me, what would be their value for infinity or nan? All right, so for exponent, okay, and then, all right, so this is not a number. Is that what you wanted? Yeah. Or you want 0 for fraction? Okay. Positive infinity. 7f8, and I just reset my program, and I have 7f80 and then 4 zeros. I think that looks good. And let me clear a previous output. And of course, an infinite temperature. My simple program says it's still not too bad. It's warm and comfy. I would probably disagree, but yeah, toasty, exactly. That's infinity. That's not a number. Okay, that's infinity. Right, and if you look at what my program does, it just compares the temperature with freeze, which is 0, okay, and then anything above freezing, it considers to be not too bad. Anything below freezing, it considers to be cold. Yeah, so that's that's a very simplistic view of the world, but it works in some cases. All right. All right. So, and then, of course, you can do floating point array multiplication. Okay. So here is their, a very common problem where you multiply two matrices and then you add x. So we have 32 by 32 matrices, and x, y, and z are all matrices. Okay, and we in this case use double precision 64-bit elements, and this is their C code. And as you can see, it's a triple loop, so it's kind of similar to what you were doing with matrix multiplication, but it's it's a triple loop, but their computation is slightly different. It is x plus y times z, right, for 3 matrices. So this is C code, and this is the example of the MIPS code. And setting up all those 3 nested loops is, should be nothing new to you. After you've done mult for the homework, I think you all got that done, and you just need to make sure that your offsets are now 8 bytes. okay, because we are using double values, and that's the only really reason. And then you need to remember that you need to, instead of loading into your general purpose registers like your T's or your S's, you load into those F registers, and so you have load D. So here you don't even need to specify double or word, because because you're using this dot D, it assumes that you want to load a double word, so 8 bytes. And so you load into F4. Basically, you just need to decide where you store what. And so of course, for X, Y, Z, and IJK, you use your general purpose register, not their CP1 registers. But for the partial results of floating point operations, of course, you need to use F registers. Okay, so and here we load into F16 from memory again. So that's their value of Z. The first one was the value of X. Okay, and then we finally here load into F18 our Y. Okay, and then we multiply and we add. Okay, because we first multiply Y and Z, and then we, keep accumulating. Okay, in F4, and there should be, of course, a $sign here. Okay, and yeah, that's pretty much it. When we are done, we need to store our values back into X, right? Because we are writing to X. So we are storing from F4 into X. We are performing this this assignment. All right, so accurate arithmetic, why we care about it, and what this standard IEEE 754 offers us to perform accurate arithmetic. It's not at all a trivial problem. So I've seen a book that is dedicated entirely, and it's a pretty thick book that is dedicated exactly to performing floating point operations so that the results are the same on different platforms and different hardware. It's not a trivial task, and IEEE 754 made this task actually a lot easier because it defines a common standard. So we're not going to go into very deep detail, but among the features that it offers is using extra bits of precision. So when we say that there are just 32 bits for the entire floating point representation of a single precision value, it's true, but internally operations may be performed with additional bits. So those are guard bits and round bits and sticky bits. Again, I'm not going to go into detail. It's really out of the scope of this class. Unfortunately, it's a very exciting and useful topic if you really doing things like scientific computations or anything like that, anything where the precision and reproducibility of results is important. Then of course you need to look into that. But for less less fancy tasks, right? Less many common tasks do not really require that level of of understanding of floating point arithmetic. All right, and yeah, so not all floating point hardware implement all of those options. So it's up to the implementers. It depends on both the hardware and the programming language. And as we discussed, some of the languages don't even offer you an overflow for integers. So it's a trade-off. That's the right word I think they're using here. In the textbook and in the slide, it's a trade-off between their cost, performance, and that's pretty much it. Cost and performance, right? You can go with much higher performance at a higher cost. If you think the market will buy your product at that cost, that might be a way to go. Or it's hardware complexity is really the cost, right? We can do a lot of stuff by just throwing in more hardware, and it just makes things more expensive. Okay, so hardware complexity by itself is is just another facet of this balance between cost and performance. All right, sticky bit. When you press Shift key 5 times fast, well, yes, it's called sticky bit in Windows. No, this is different. This is not that sticky bit. It's a totally different thing. But good memory, yeah. All right, I'm glad you have some associations with the word sticky. Sticky bit is actually used in Linux, Unix. All right, I don't know if you noticed when we were talking about permissions, I kind of ignored this sticky bit, but there is a permission called the sticky bit. Okay? And of course, it has nothing to do with the Shift key on your keyboard. So it's the third context in which sticky is used in computing. Okay. All right. So with subword parallelism, and let me just see what we have. All right. So let's go through. Oops. For this part real quick. We're not going to go into much detail. It's basically a very soft introduction into what lies ahead of us, and that is the discussion of parallelism as one of the main methods of increasing performance. So for many applications, you can structure your computations such that instead of multiplying scalars or single values, you can multiply or add or perform any other arithmetic on vectors, right? So vector is just a bunch of values packaged together in a single data structure. And if we are somehow able to perform operations on vectors quickly, or at least faster than operations on each element of the vector serially, it would be a big performance advantage. So it's called simultaneous operations on vectors. And it turns out that yes, we can actually build hardware to do this, to perform operations on vectors very efficiently. So for example, we can have an 128-bit adder that can perform either 16 additions on bytes or 8 additions on double bytes or 16-bit values or 4 additions on words 32-bit values, if we say that a word is 32 bits. Right? The byte is always 8 bits. Well, I'm lying to you. History knows 6-bit bytes and 7-bit bytes, but it's pretty much history. So currently, you're not gonna probably encounter 7-bit or 6-bit bytes. Your byte is going to be 8 bits always. Well, for now at least. Okay, but for the word, the definition is it depends on the architecture, right? So if we are in a 32-bit architecture, then the word is 32 bits. If the architecture is 64 bits, then our word would be a 64-bit thing. So this is, the ability to work on vectors is one of the mainstream methods of increasing efficiency, and it is called SIMD, single instruction multiple data, where multiple data means that in a vector we have multiple data elements like that. Okay, and then if we multiply vectors 7 0 1 5, I don't know, in one operation, of course it's going to be more efficient than multiplying each the values one by one, and then performing operations on individual elements. Okay, and that's why it's SIMD, so single instruction like multiply on multiple data elements that we can think of as a vector. All right, and well, yeah, that's invalid mode. Yeah, I know. So we need to have like that. Okay, is that better? Okay, good catch. Good catch. You are paying attention. You are a great class. All right. So x86 architecture also uses a co-processor, at least the traditional x86 architecture in the original design that was used for first IBM PCs. It was actually a physically separate coprocessor called 8087. So the main processor was 8086, and the coprocessor was 8087, and it has 80-bit registers, so 8 of those registers. Why 8 bits? You might say you only need 64 bits even for double precision. Well, that's one of their measures to increase precision, right? Because internally all operations were performed using 80 bits, not 64 bits, just to avoid losing precision too early. Of course, it looks like a great idea, but in fact, it causes a lot of problems. Why? You might say, well, because imagine you have two systems. One uses this 80-bit internal registers for floating point. Another one uses 64 bits as prescribed by the standard. You perform the same set of arithmetic operations on the same values, on the same arguments, and the results might not be the same. So there is a problem with reproducibility of operations, and that is a huge problem, right? Because imagine you run your simulation on one machine, it gives you results slightly different than the same simulation with the same data on another machine. It's very bad. It's a big problem. So that's why the more current processors, they actually have they have a configuration bit that allows either to use their hardware to its fullest potential and the fullest precision, or to just stick to the standard. If you are using Java, you might look up this keyword, strict FP in Java. That controls exactly this. So some programming languages allow you to have some degree of control over this, right? So strict FP means, oh, even if hardware is capable of doing more, we just want to stick to their standard, to IEEE 754, and not use any extended features not in the standard, just to ensure that the results are reproducible on another machine that adheres to the standard, right? So, and of course, by default, if you do not specify this keyword, then you would just use their, all their registers, all their features that your hardware offers you to, to get their highest precision of floating point operations. And so in 8086, registers are basically, they are a push down stack. So push down stack is LIFO, okay? And that means that the last item that was pushed in the stack when you uh, when you take it out of the stack, their last item that was added is removed first, and then the registers are actually indexed from the top. So ST0 is the top one. They're the one that was added the latest, and this index 0 corresponds to how deep from the top. This is their top. This is one below the top, and so forth. All right. So again, like I said, we're not going to go into much detail about 8087, and one thing that you might want to remember is that it was actually, by today's standard, it was given very poor floating point performance. It was very slow. Even by that day's standard, like early 80s, it was not the best, but overall pretty pathetic, right? But it was good. Okay, so, and if you read the journals of magazines from that time, you would see, oh, you could install actually, and you could buy this coprocessor separately and install it, and you would get a much higher performance with their 87 processor than without it. Because if you only have 86 CPU and no coprocessor, then guess how all your floating point operations are performed? They're just performed, by running many instructions in software, right? So basically, software generates integer arithmetic code to perform your floating point operations. So there is a math library that performs floating point operations using only integer instructions. And of course, it's very inefficient, right? It's much slower than any coprocessor. So 87, at the time was a blessing. And we only say it's poor performance compared to other floating point coprocessors. not compared to emulating a coprocessor with integer instructions. All right, and those are their x86 floating point instructions. Again, I'm not going to be asking this on any of the exams or anything, so we just going to skip this. And much later, there were extensions to the ISA of x86. So there were additional instructions that were added to perform those essentially vector operations, SIMD, single instruction multiple data operations. And here they are. They were called streaming SIMD extensions, SSE2, and we will talk a little bit more about them later when we discuss parallel programming and other measures of increasing performance. So for now, we just need to know that it adds registers that are much wider than traditional 32 64-bit registers in x86, and so those are extended registers that then can be used in different configurations to perform floating point operations. So they can be treated as two 64-bit registers for double precision or four 32-bit registers for single precision. Okay, and instructions can operate on those multiple data elements at once. Okay, yeah, we are almost done. So matrix multiply. So that's again. So DG EMM stands for. So this D is for double. This GE is for general. And MM, you know, it's matrix multiply. So it's a standard task. Yeah, yeah. I will save 2 minutes to talk about what is included in the exams. Okay, in the next exam. Okay. So, and actually, why? All right. So, matrix multiply. Let me see. Yeah, we can finish this and then talk about the exam. All right. So. Matrix multiply, this is your standard triple loop. This is something that you've done in your homework, right? So we are computing C, which is A times B in terms of matrices. So C is A times B, right? And it's a very common task. That's why it's part of many benchmarks. And so note how this is unoptimized code, our straightforward C code, like something that you would have written in your homework. And this is actually an optimized code. It's still C, but if you include this header file called intrinsics, that gives you access to C functions that would generate those SSE2 instructions. So those instructions. Okay, so it's effectively like writing assembly code without really writing the whole thing in assembly, but just saying, oh, please use, for these instructions, for these addition, and please use their vector instructions. Okay, so you see, it is technically a C function, but when it is part of this intrinsic header file, and it is declared in that intrinsic header file. And note how we need to load stuff differently and store stuff differently. Okay, and then we can perform addition. All right, so this optimized C code will translate into this assembly code where we would use, as you can see, single instruction to perform an operation on the entire vector. Okay, and how do we know it's a vector? See how we increment I not by 1 but by 8. So our vector is of length 8, and same here in assembly code. We see that we are advancing our register by 8 because we are multiplying their values 8 at a time. And this code, of course, is much faster than your standard code. All right, so we're going to stop here. So to answer your question, What is left to discuss here? And there is one. Oh, there's actually what? Well, turned out we didn't have any submini polls today. Well, we're going to have them next time, okay? So they are both in the remaining part of the slide. So for the exam, we will stop here. So 72 is our last slide, but we didn't cover this first part, which is up to slide 17. Okay, so on the exam, we're going to have from this slide 18 and all the way to slide 70, was it 72? Yeah, 72. So as far as 3B is concerned, that would be the scope. And of course, whatever was left from 3A that we didn't cover on the last exam, that is going to be also included. Do I think I'll run an exam review again? Okay, we can do that. I think attendance was much better last time than it was the first time. So yeah, I'll put a post. I'll put a submini poll, and find what time would work for people best again this time. Okay, yeah, if you need it, I can totally do it. And don't worry about x86 stuff. It's not going to be on the exam. It's really for just fun and general information. Don't sweat over x86. We didn't really go into any kind of level of detail that would allow me to ask questions on x86 on the test. All right, so yeah, 1:51. Our time is up. Sorry for getting 1 extra minute out of your time. Again, enjoy your Friday. Oh, it's Halloween this weekend, right? So yeah, happy Halloween, folks. Yeah, do something fun, okay? And yeah, enjoy your weekend. Enjoy the rest of your day, and I'll talk to you on Tuesday. Thank you. Have a great day.